started. Oh, forgot to turn my mic down. Yeah, so to be clear,
I didn't realize that.
yeah, I did, last time I did cover 5.1 and I think most of 5.2. We didn't do the final example in class, but I'm going to get right into 5.3 today. But let me first read you the email that I got. I'm not going to read it word for word. This morning from Ms. Bradshaw. I'm supposed to apologize for her for not being here. She hates to miss class. She's hoping to be back tomorrow, and she will make any adjustments to the schedule, you know, depending on what it is that we covered. So I guess if she is well enough tomorrow to come in, she'll be here. If she's not, it'll probably be me again, just because consistency. That's the reason I did it today. It could have been anyone, but I figured since I was here before, it would flow a little better than having, you know, two different subs. So, yeah, that's it. All right? Good?
Did she give you our review?
No, this is all she gave me. Do you have a test coming up?
Yeah.
On Monday? On Monday, yeah. So, and you only have class again on Thursday or on Friday? Just Thursday. My guess is that she won't test you on Monday. That would be my guess. Let me. Yeah, that would be kind of tough. Yeah. So, I will. I'm recording right now. I will say on record that I am suggesting, you know, that she not test you on Monday. That you do something just to make you feel a little more comfortable. Okay. But we're going to get down. We're going to get down to business today. I was able to get notes for today's material, 5.3, and I was also able to. Hello. Everyone has the notes on the table? Do we need any extra notes? We're okay? I was actually able to prepare a little bit this morning, which is more than I had yesterday. I only had like 10 minutes. So this morning around 8 o'clock, I was able to put together a little something that I hope will help you see what's going on here, all right? So I want to start off class with this. All right, let's say, and what I'm getting at here is the last problem on today's handout. And we'll talk about it when we get to it. But first, let's just say that we are a company and we manufacture tables and chairs, all right? And we are going to charge $90 for a table, for one table, and we're going to charge $25 per chair, all right? Then can we write up a profit function for this?
Yeah, sure.
Okay, what would it be?
90T plus 25C, right?
Okay, hold on.
90X plus
90X.
Can we use X and Y just because we've been using X and Y? So,
That's cool.
all right, so let's let X be the number of tables, right, that we're going to manufacture and sell. Y is the number of chairs, right? Then the profit we could call P would be 90X
Plus 25Y.
P90X, look, plus 25Y, right? That's what this would be? Okay. So what I'm about to show you right now is, I can almost 100% assure you Ms. Bradshaw wouldn't show you this way, okay? So there's a little variation. I know it's in my nature, this is the way I have to do it. All right, so look, let's just take, for example, some values of X and Y to figure out profit. So let's say I picked this point right here, which means I would manufacture and sell 0 tables, right, because X is tables, and 0 chairs. So what would my profit be? 0. So how can I write this? At 0, 0, we get that P is 0, yes? How can I represent that graphically? You see, I already have X and Y to represent the number of tables and chairs, right? So where in my picture could I represent the profit? Just sit on that for a second, okay? Think about that. So let's try a different point. Let's say I make, let's go 10 and 5. Okay, so what about this point right here? So that means I'm going to make at 10, 5, I'm going to have 90 times 10, right? Plus 5 times 25, or 25 times 5.
Yeah.
And what would that be?
1,000.
Someone's doing that for me? Okay. Y'all okay with that? Understand? No questions? No? Okay, so for this point right here, I know my profit is 1,025. Here my profit is 0, right? How could I represent that graphically? So check this out. This is what I'm going to do. Imagine, if you could, that this is, instead of a flat sheet of paper now, I want you to visualize it as having depth, another dimension to it that comes out of the page. And so when I plug in 0 and 0, my profit is 0, right? So I actually don't want you to come out at all because the profit is 0. Understand? But at this point, I actually want you to walk straight out towards you 1,025 units, which is somewhere way out there, right? Understand? And then for the next point, whatever we pick, right? For each of these points, imagine some value coming out, right, at you. Y'all getting this? So for every point in here, you have all these values, yeah? So three-dimensionally, it would look like this. And don't worry about drawing this because this is just to get you to visualize what's happening, all right? Imagine I don't know if y'all can see this. Maybe if I draw it this way. Imagine taking this right here and turning it and laying it down on the ground like this. Do y'all see that? And then this was the 0 that I plugged in, 0, 0, and I didn't go up at all, did I? And then here I went up 10, 5, so I go out 10, which would be about here, and then 5 would be about here. And do y'all see that point sitting on the ground? Do y'all see that one? And then what I want to do is measure 1,025 units straight up, and I'll even connect it with a line so you can see, like that's the height, that's your profit. Do you see it? If you put all these different profits together for all of these points, what you will create up here, all these points together, will be a flat sheet of paper, like a plane, like a three-dimensional, whoa, you all right? Like a three-dimensional page. Is the chair dead?
Yeah.
Okay. We have an extra one. Can y'all see this? Can y'all kind of see? Now I'm going to have a way better visualization for this in a second. But the thing is, once I turn the projector on, I have to let it cool off and then turn it back on. So I'll show you this in a minute. But I want you to start thinking about this, that this right here are all the different combinations of the way we could make tables and chairs. The profit is going to be visualized as some surface sitting above it. Y'all on board with this? Okay. What would we be interested in? We would be interested in something like, where would we have the maximum profit, right? We want to make the most money. And so what we're going to be trying to do is like find the highest point on this sheet up here. Like, where does it occur? All right? So now let's read through today's notes. Linear programming. Linear programming in 2 dimensions, a geometric approach. So when we say linear programming, we're talking about a specific type of problem in business. Specifically, we're talking about where we have like profit functions that are linear. Like the last one we just had, right, that I put up here, it was 90x plus 25y, right? That's what it was. This is a linear programming. This is perfect for a linear programming setup because this is linear, isn't it?
Yeah.
Okay. So we can read through this, and I think Ms. Bradshaw told me that usually she says, don't worry about all the math. She's just, I mean, all the language, she's going to kind of make it make sense up here. I think we can talk a little bit about this without going, blowing our heads up. This function right here, the profit function, the one we're trying to find the highest value of, right? Like profit, we want to know the most profit we could get, right? If this was a cost function, let's say we have some cost function, which was like 5x plus 10y, something like that. we would actually not want the highest point on this, right? We would actually want the lowest point. Understand? So these two, whichever one, depending on your situation and your problem, these are called objective functions. These are the ones that you're either trying to find the maximum of or the minimum of. And on that sheet of paper, the max would be the highest point, the minimum would be the lowest, right? But this sheet is the objective function. Now it turns out, I'm looking at theorem 1, that if you have an optimal solution, all right, if the optimal solution exists, it must occur at a corner point. So last class, remember we were talking about graphing systems of linear equations, linear inequalities, and we would have like one line did this, one line did this, and then we would try and find that feasible region. And we talked about corner points, and just barely at the very end, I told you these points are called corner points, right? Well, imagine now again that these are the only points you're allowed to plug in. And you're going to have a sheet sitting above this, all right? The maximum that you're going to get, or the minimum, again, depending on this, has to occur at a corner point. That is a theorem. That means it's proven that that's true, which means these corner points are absolutely essential for us to be able to solve problems. We have to be able to find these points. Understand? Now, let me try and show this to you with a picture. Because I think if I show you the picture now, it'll help us going forward. And I want you to take a look, while I'm getting the projector fired up, I want you to take a look at example 1 here. I'm going to write it on the side since you have it. It says find the maximum of p equals 3x plus 2y. So we're not talking about the tables and the chairs right now. Okay, this is some other model. And then they give you subject to these constraints. And everything that you're going to see here is that thing coming on? Come on. There we go. Everything that you see in this brace, that look familiar to you? That's what we did last class, right? And the homework? Okay, so we know how to do this, right? What this is going to create is our two-dimensional feasible region. Then what we're going to say is if you can only plug these points in, if these are the only ones that are allowed into the profit function, find the highest point. Understand? So here comes my visual. It's going to take a minute. I'm going to have to kill the lights. Ooh, nap time. Okay, so I was able to put this together before class to help you see it. Okay, so what we have here is, I've already done all the work, okay? We're going to do it by hand, all right? But I just want to show it to you first. So we graph this blue one right here is this inequality, right? And the region is actually this way, okay? So that I shaded from here down. And then this one right here is this one shaded down. X greater than or equal to 0 is this shaded over, right? X bigger than or equal to 0 means X values are bigger than or equal to 0, right? Y values greater than or equal to 0 means everything was shaded up. And so do y'all see where the feasible region is? Yes? Right there. That's your feasible region, okay? So imagine the rest of it's not here. And now you're asking, plug these points into the profit function, which was, in this case, 3x plus 2y. Do y'all see that above this would be a sheet? That's hard to see, right? Maybe? So actually, oh, and also let me label the corner points. These are the corner points. What we know is that our maximum should occur at one of these corner points, yeah? So I'm going to show it to you visually, three-dimensionally. So here's that sheet of paper. If you look at it from the top, it looks like this, right? Understand? Now I'm going to tilt it sideways so you can see it. If I take every point and draw it up, 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 I get what we call the objective function, which is this surface sitting above it. Do y'all see that?
Yeah.
And what we want to know is, where is this red surface the highest? Can you tell where it is? Let me bring it from the top first. If I look straight down on it, come on, Robert. it's hard to get right straight on, but can you kind of tell if I tilt it back?
Yes.
It looks like it happened at that one, right? And we're talking about that height, right? From here to here would be our maximum. Okay, understand? Does that make more sense this way now? Now, you're not going to have to draw it three-dimensionally or anything like that, but I want you to understand how this is connected to this. This is just a surface sitting above your feasible region. We're trying to find the highest point on it. Thanks to the theorem, all we have to do is find the corner points and test them, check them. So what we're going to do right now, is we're going to go back to this first one right here. We're going to go through the process of getting the feasible region. We're going to actually find it, shade it in. We're going to find the corner points. And then to actually figure out where the biggest value is, we're going to take that corner point, plug it into P. We're going to take that corner point, plug it into P. We're going to take that corner point, plug it into P. That corner point, plug it into P. They're all going to spit out answers, aren't they? The biggest value we get out is the maximum profit. Got it? Into the P equation. Yep. So all the work we do first is all of this, and that's last class. Okay? Then once we figure out our corner points, we plug them into P. The biggest output we get is the max. And if the problem was asking for the minimum, then we'd be looking for the smallest value. Geometrically, it just corresponds to finding the highest and lowest points on that sheet of paper that's floating above our feasible region. Yeah? Okay. All right, I'll leave that on the board. I'm going to turn the projector off because it causes issues. All right, so my goal, and let's see how much time it takes. My goal is to do example 1 and then the last problem, which is the word problem. If I can do both of those today, we're good. And then I'll leave you to do on your own example 2 and example 3. Because these do take a while. So let's look at example 1. Maximize that function. Subject to the constraint. We call these constraints. First, part A wants to is going to be my graph. Let's take care of some of the easier ones first. Y is equal, y greater than or equal to 0. That's what? Solid line, right? Crossing through the x-axis like this. I don't want to go right on top of the x-axis, but this would be the line. That would be y equals 0, wouldn't it? If I turn that into an equation, y equals 0. We graph that. Once we graph that, remember you pick a test point. We don't need to for this one, right? Is this too easy? This one, you know which side's shaded? Y is greater than 0, so up. Now instead of shading, which becomes kind of a pain in the ass to kind of keep up with all this different shading, what we can do instead is draw little arrows up like this, just to let you know we're going to shade that one up. So anything on this side of the line works. Okay? With me? All right. The next one we're going to do, x greater than or equal to 0. I'll do this one in green. X equals 0 is the y-axis, isn't it? And so I could draw this one. And greater than means to the right. Yes? So I'm going to draw little arrows this way. Like that. Instead of shading the whole thing. It's fun, right? Never thought you'd be able to, sit there and draw these little cute arrows and stuff. All right, now these two, how do we do these? Give me just the basic steps to how to graph this thing. First go ahead and set it equal to 0, right? Graph that line. Solid or dashed? Solid. Solid. And then pick a test point, shade that side, whichever side, depending on the test point. So let's go ahead and write that down as an equation first. 6x plus 3y equals 24. I'm going to solve this for y so that I can use the slope and intercept. So I move the 6x over, negative 6x plus 24. Then what? Divide by 3. Y is equal to what? Negative 2x plus 8. Thank you for the response. That's what I need. All right, so I can go graph that now? So I'm going to go up 8 on the y-axis. So I don't know yet. I'll just say this is 5. I'll say this is 10. So 8 will be about right here. And then I'm going to go what? Down 1. No. Down 2 over 1. Down 2. Oh, careful. 2 over 1. Negative 2 over 1. That's all right. And get another point. Right? And I can do that and draw a line. But even though that's great, wouldn't it be even better if I just had the x-intercept? Like, if I just had the point where it hits the x-axis, wouldn't it be easiest to draw the line through? How could you find the x-intercept of this? Find the x-intercept. You plug in 0 for what? Let y be 0. So it's opposite. If you want to find the x-intercept, you let y be 0. If you want to find the y-intercept, you let x be 0. So let's let y be 0 in this equation. What do you get? I'm out of room, so. X is 3? You all with? No? Is that right? Sorry. If we let y be 0, I'm coming back up here. You get like that. This is gone. So 6x is 24. So x is 4, right? So if y is 0, x is 4. So that's a point, 4, 0. And that would be, I don't know. I'm just going to say maybe this is 5. This is 4. Is that okay? We okay with that? You happy with that? And I'm going to draw what here? Solid line. Are we done? Which side do I shade, right? That's what I need to figure out now. So how am I going to figure that out? Test something, right? What would you like to test? 0, 0 is probably a really good one, right? Because it doesn't lie on the line. And we are going to check that where? Where are we going to test that? Into the original inequality, right? So we plug it in there. Let's see. We plug in 0 here, 0 here. We just get 0, don't we? Is that less than or equal to 24? Yes. So 0, 0 is on the correct side. So that means I want to shade down, right? Like this? Like that? Okay, what I'm going to do is I'm going to put arrows like this. What do you think our feasible region is going to have? Like in terms of these arrows, our feasible region will be where all the arrows point, right? Like this couldn't be a feasible region because these arrows point towards it, but the blue ones don't. Do you see that? So our feasible region will be where all the arrows point. But we still have one more to do. Are there any questions? No? Okay, let's do the other one. I'm out of colors, so I'll just have to go with black. Okay, so we're going to go through the same process on this one. Well, we first turn it into an equation. Let's take a quick vote. How many of you like, or I shouldn't say like because you probably don't like any of this, but how many of you prefer to do solve for y and then go up and do slope? Yes? How many of you prefer to let y be 0 to find the x-intercept, let x equal 0 to find the y? I like that way too, but you should be comfortable both ways, right? I'm going to do this by the second method. So I'm going to find the x-intercept first. How am I going to do that? I let y be 0. If y is 0, I get 3x is 30. That means x is 10. So I have a point here, 10, 0, right? That's the x-intercept. No? Ask a question. Okay, so if
you just got rid of y. Okay.
yes, because y is 0, this kills it off. That's all right? And how do you find the y-intercept? Let x equal 0 this time. So if x is 0, it kills this off, and you're left with 6y is 30.
Could you have done that to the other one we just did?
Yes.
Okay.
Yes. That's what I'm showing you both. Actually, that's how I got the 4. This right here. Instead of going like down 2 over 1,
Oh, okay.
I actually said, you know what? It'd be better if I actually knew exactly where it hit down there. So that's what I did.
For a better visual, I saw a video where they did a visual on that.
Mm-hmm.
That's the way I'm doing it now.
Uh-huh.
But they put their hand completely over so that you could visualize.
This, like x is gone, right?
Right.
Yep, x is gone. When x is 0, that's gone. And you have this remaining equation, which is this.
And then if it's a negative, that's when we change the sign.
Over here, if it's a negative.
If it's a negative, change the sign instead of less
But see,
than.
I'm not working with an inequality. Careful. I'm not working with an inequality. I'm working with the equation, right?
But it's a positive.
Yeah. Okay, so it's positive 5 for the y-intercept. So this is a point, this is the point, what, 0, 5? Y'all all right with that? So let's plot these 2 points, 10, 0, and 0, 5. So 0, 5 is nice. It's right here, right? And 10, 0 is out here. If this was 5, then this is probably 10 out here. And we draw a straight line through those points. Any questions yet? Any questions yet? Solid line. Okay. So we need now to figure out which side of that line to shade. So test 0, 0 again. Oh, he was telling me it gets loud over there. Do y'all hear noise from over there a lot? It's a fun class. They're doing like video editing and stuff. Not as fun as this, but still fun. All right, so test 0, 0, does it work? We're testing into here. So if you plug in 0 and 0, the left side goes to 0. So you get 0 is less than or equal to 30. As far as I'm concerned, that's true, which means we're going to shade down, right, like this. Again, I'm going to use arrows. Little arrow, little arrow, little arrow, little arrow, little arrow, little arrow, little arrow. All right. Do you see the feasible region? Yes? Let's rule out some regions. Why can it not be this region right here?
That's not where the intersect.
Which one is not shading this way? The black one goes away from this, right? So it can't be that one. This one right here, why can't it be this region? The blue is shaded away, right? Can't be up here because, well, both the black and the blue are going away, right? This is the only region right here. This is the only region that all arrows point towards. Yeah? So now let me kind of blow that region up a little bigger so we can see it. And draw it again. I don't need all that other junk there. We can look and we can kind of pick up the corner points already. Like, do you know this point right here? 0, 0. So I do have one corner point I know for sure. 0, 0. And then this one right up here, right? Where is it? At 5, right? This point right here. This is the point 0, 5. I have another point down here, don't I? 4, 0. Like that, right? So I've taken care of these two and that one, right? There's only one more corner point, isn't there? Right here. And we need to find it. Agreed? To find it, we need to realize it's the intersection of the blue line with the black line, right? So we come back over here. This was the blue line. This was the black line. I need to set up a system of equations, not inequalities, linear inequalities, system of linear equations to solve that. So that's what I'm about to do. May I erase this side? Okay. So now I go through and I'm going to find this corner point by solving the system 6x plus 3y equals 24 and 3x plus 6y equals 30. And we talked briefly about this last class. You know, how would you go about solving that? Elimination, right, was one way, and substitution was the other way. So are we going to stick with elimination here? Elimination. How would you eliminate? Do you want to eliminate the x's or the y's? You want to do x's? How would you do that? Multiply the bottom by 2? Negative 2. Let's multiply the bottom equation all the way through by negative 2, because that'll make that a negative 6x, and when we add it straight down, it'll go away, right? That's the idea. So I'm just going to rewrite the system. If I'm using different notation than you've seen, then I apologize. These are the slight variations in the way things are done. Right? That makes sense, though? Now you can add straight down. Did I distribute properly? Everything got the negative 2, right? So add this down. X's are gone. You get, what, negative 9y equals negative 36. Boy, I'm glad it's a multiple of 9. Because if it was a fraction, then that would just, what, suck. I mean, it wouldn't be like the end of the world. It would just not be fun. And in the real world, the chances this is going to be a nice integer like this is pretty rare. But all right, so y is 4. So y is 4. Once you know what y is, you go back to get x, right? And you can use any equation, any of these. Doesn't matter which one. You want to use this one? Right here. Okay. That's your choice, right? So I'm going to rewrite this. I'm going to substitute y is 4. So 3x plus 6 times 4 equals 30. Understand that? 6 times 4 is 24. So 3x plus 24 equals 30. Subtract 24 from both sides. 3x is 6. Divide by 3 on both sides. X is 2. So we have the point 24, don't we? X is 2. Y is 4. Do we have any questions? We're all good? So 2, 4 would be, what, here's 2. 4 is about right here, so I don't know, somewhere in there. And now I could come through and I could just like connect everything together with straight lines. And I could shade this in. Let me make sure I label that other corner point. This is the corner point 2, 4. These are my x's. These are my y's. Feasible region. Part A is done. Okay? We're all right? Yes. Uh-huh.
Yesterday we were doing like a 3 line. Would there be any situation where instead of having just 2 lines, you would have to try to find a center point for 3 lines?
Yes, that could happen. In fact, the last example, part B of today's last example, will have 3 lines. So we'll do an example of that. All that would happen, as you'll see, is let's say we have one line that does this. Let's say we have another line that does this. And let's say we have a third line that does something like that, okay? Then if we put our arrows and stuff, we'll probably get a feasible region that's in here. And so we'll have 1, 2, 3, 4, 5 corner points. See them? These 3 will be easy to find. This one would be the intersection of the blue and the green. So you would do the same thing we did for 2 of them, right? This one would be the intersection of the red and the green, so you would do another 2. So you'd have to know which is which. Does that make sense? Okay. And then what if you had 4 lines and 5 lines? And you could have a crazy-ass region that's just made up of all these different lines. All right. We're not done with the problem, are we? That's only answering part A. Graph the inequality. Find the corner points. Oh, we've done B already, haven't we? Okay. So part C, test the corner points in the objective function. So don't forget, the whole point of this was to figure out where this would be the biggest, right, and where it would be the smallest. In this one, they wanted the maximum, right? So all I'm going to do is take all my corner points and plug them into that P function. So let's start out with, let's see, here are our points, 0, 0. Doesn't matter what order we do, there's 0, 5, 4, 0, and 2, 4. I'm going to plug each of these into P, right? Yeah? So sometimes we write it like this, meaning like P with 0, 0 plugged in, P with 0, 5 plugged in, P with 4, 0 plugged in, P with 2, 4 plugged in, and just see what it's equal to. Is that all right notation-wise for you? So this would be 3 times 0 plus 2 times 0. So just replacing x with 0, y with 0, which is 0. All right, next one would be 3 times 0 plus 2 times 5, which is 10. So far, that's the winner, right? Keep going. 3 times 4 plus 2 times 0, which is 12. Now we have a new winner, right? Then we do our last one, which is 3 times 2 plus 4, 2 times 4, which is 6 and 8, which is 14, right? Which is 14. We good? So where does P have a maximum? At the point 2, 4. So when x is 2, so I'm summarizing here. P equals 3x plus 2y has a maximum value of 14 at x equals 2 and y equals 4. Right? That's the conclusion. If x is 2 and y is 4, this thing is the biggest it's ever going to be on that feasible region. If you go outside that feasible region, then that's a different story. Right? We're just looking in that feasible region. I'd like for you to look at the notes and look at theorem 2 real quick. I'm going to read through this. It's called existence of optimal solutions. If the feasible region for a linear programming problem is bounded. So you see this region that we had just a second ago? Looks something like this. This region is bounded, right? Meaning that it's, you draw it, it has sides that it cuts everything off, right? It's bounded. If it's bounded, then both the maximum and minimum value of the objective function exists, right? Always exists. So look, this was the maximum, right? There's also a minimum, and it must happen. And the minimum would be the 0, right? Because it was a bounded region. But part B says if the feasible region is unbounded and the coefficients of the objective function are positive, then the minimum value of the objective function exists, but not the maximum. What? Okay, so let me just draw a picture. First of all, you have some P where you have a number in front of x and a number in front of y. I'm looking at the theorem 2 part B. If these two are both positive numbers, so like in the example we just did, they were, right?
Yeah.
3 and 2. If those are both positive, but your region is unbounded. So let's say you had a region that looked like this. We haven't had a region like this, but let's say your region was everything out here, which kept on going forever, right? Just keeps going and going and going. That's an unbounded region. If these are positive numbers, your region's unbounded, then you're only guaranteed the existence of a minimum value, not a maximum. And then C says, if the feasible region is empty, that is, there are no points that satisfy the constraints, then there's neither a maximum nor a minimum. That one's kind of trivial, but think about it. What if you're trying to find the maximum of this function, and it turns out that your feasible region is nothing? Like, let's say you get a line and you're supposed to shade that way, and you get another line over here and you're supposed to shade that way. And then they don't have anything in common, so you have an empty region. Then it's impossible for you to talk about the biggest value and the smallest value. I don't know how heavy she's going to be on asking you about that, but I just wanted to run through it. You all ready to do the last one? If we do the last one and we have time, I'll let you try one of the examples on your own. But I think I'm not going to have enough time to finish this, so. All right, so we have a table here. Everyone's got this? I'm going to try and draw this. Whoa. All right. Department, assembly, I'll just put ask because it's fun. Finishing, profit, per. Labor, hours, per unit. Table, chair, 8. All right, there we go. Everybody ready? Oh, someone needs one? You do? Okay, I'm sorry. Okay. Hand one back there. Right here. All right, so you want a business application. Here's a business application. A furniture manufacturing company manufactures dining room tables and chairs. The relevant manufacturing data is given in the table below. So here's your table. Part A, how many tables and chairs should be manufactured each day to realize a maximum profit? What is that maximum profit?
8x plus 2y.
Yeah, so let's make sure we can understand this table, right? This is tables, this is chairs. What is the 8? What does this represent? What does 8 represent?
X.
They made 8 tables. Read this. What is this right here? This is blocked together, right? Labor hours per unit. So table, 8, assembly. So what does this mean? It takes 8 hours per day to assemble a table, a single table. This means it takes 2 hours a day per table to finish it. I'm not real big on texting during class, sir, so that's all right. I always tell my students, you got something important on text, just take it outside. It's not a big deal. Okay? What is this? 2 hours per day to assemble a single chair, right? 1 hour per day to assemble a single, to finish a single chair. Make sense? I forgot to put this here. But this is not hours, right? This is what?
Profit.
This is the profit that I make per table I make, right? This is the profit I make per chair I make, right? Assemble and finish. Over here, 400 and 100. What does this mean? Maximum labor hours per day. So I've got a labor force, right? The maximum hours per day that I can actually have my people work is 400 for assembly, right? For the finishing part, the maximum I can have is 120 per day. Understand? And the most important thing is interpreting the table, because if you can't interpret the table, then you're never going to get to the feasible region, corner points, and all that stuff, right? Any questions on the table, though? Somehow, some way, we're going to get a profit function here, and we're going to get a system of linear inequalities from this table. Let's see if we can do it. What is it that we're trying to find the maximum of? How many tables, right? So how many tables? The number of tables, right? We want to know the number of tables and the number of chairs that need to be made per day to get a maximum profit, right? So there, I want to know X and Y. X will be what? What? Cost of tables, what? Read the question. How many tables, right? How many tables? So X is the number of tables that I'm going to make per day, right? X is the number of tables made per day. I also want to know how many chairs, right? So let's let Y be the number of chairs. Per day. So how many tables and how many chairs should be made to do what? For maximum profit, which we'll call P. All right, for profit? So look at this problem we just did before. We had P was the objective function, wasn't it? And we assumed it was profit. So we actually have this exact same setup over here. We have X and Y, right? We have profit, and we're going to have some constraints, right? We cannot manufacture 100 tables. Why? Why can't we manufacture 100 tables a day? Because that would take 800 hours, right? And I'm only allowed to have 400 hours. So there are some constraints here, aren't there? There's some restrictions. And these are all restrictions, right? Inequalities restrict you. So what we need to do is figure out all these different pieces. What's P? What are the restrictions? So you want to start with P? Okay, what's profit? What is the profit we would make? $90 times each table I make, right? Plus 25 times each chair I make, yeah? So let's write that out first. The profit is going to be 90x plus 25y. All right, now, moving on, let's try and come up with some restrictions. That's the objective function, right? That's the objective. So what are some restrictions? Anyone want to give me a restriction? 8 times x, right? 8 times x is how long it's going to take to manufacture 8 chairs, right? 8x plus 2y, which would be how long it takes to assemble my chairs, must be equal to 400? No, less than or equal, right? Just because I have a maximum of 400 hours to work, I definitely don't want to reach that maximum, do I? Then I'm paying my labor force for all 400 hours. It'd be nice if they didn't have to work that much. So let's see, 8x plus 2y must be less than or equal to 400. That's one restriction. And then for the finishing, 2x plus 1y must be less than or equal to 2x plus 1y must be less than or equal to 120. Any other restrictions? X is greater than or equal to 0. Y is greater than or equal to 0. Now those two seem obvious, but you may forget to put them down. The number of chairs and tables you make must be either 0 or a positive number. Yes?
That's exactly what you're asking.
Yep.
Why you got the 0.
Yep. So it wouldn't make sense to have x be negative 2, right? Any other restrictions? I don't see anything else here. You all understand that? Okay. So now we go about the business of finding the feasible region in here, drawing it out, and okay, so let's do it. Should I go a little faster since you kind of got the idea of what we did in the first example? All right, so here's what I'll do. I'll take care of these two. Y is greater than 0 is this. X is greater than or equal to 0 is this. And then let's do this one. I'm going to draw a line, right? Draw a line. It's going to be a solid line. And I'm going to shade one side of it. So to do that, what I've been doing and what you all agreed you liked and preferred, switch it to an equation. Find the x-intercepts first by letting y be 0, right? What's 50? What?
X.
Oh, okay, sorry. If y is 0, x is 50. So 50, 0. I'm not showing the work for that. The y-intercept, you let x be 0 and you get 200. Everyone agree? Those of you following along? Do I need to show that or can I go? I don't mind showing it, but you're all right? Okay. So I'm going to plot those over here. 50, 0 would be, I don't even know yet. I'm just going to call that 50. How about that? And 0, 200, I don't know, way up here, 200, is that all right? Now, I hope the next line isn't like 500 or else I'll be way up there. But yeah, I already did this, so I know what's going to happen. But if that happened, right, if that happened, what I would do is probably redraw the whole thing. Just start over. So I'm going to do this. I'm going to shade. So I pick a test point now, right? When I do that, it's going to shade in. So 0, 0 is going to work. Okay? Then we do this one. Find the x-intercepts.
Y equals 120.
So you just want me to just say what they are?
0,
So 0, 120, and
60.
60, 0. Do I get a second on that? Yes? Okay. So 0, 120, good thing is right here, somewhere around there. And 60, 0 is on the other side of this. So 60 here. And again, on this one, when you test, it's going to be inside. And so do you see the feasible region? Right in here.
Is the corner, the last corner of the number 50?
50, yes? This
No,
corner?
The last corner, the last box in the table.
Is
The
the-
last corner, the maximum, that's the one.
This one right here?
Yeah, that one goes in the last box, right?
In the last box?
On the table?
I'm not following you. It goes in the last box?
Yeah, on the table, on the paper.
Mm-hmm.
That corner goes in that box, correct?
Yeah.
I don't know if I'm explaining myself correctly.
Does it, yeah, anyone know?
Variable for the table, like the maximum number of hours, if that point right there would, like, once you put into the equation, find the answer with that, go into the last box for the max hour.
Is this, I still don't get it.
on the table,
Like right here,
Oh, yeah, to fill in, oh, this table, okay.
Would that corner be that number?
Profit, no, because that last corner doesn't make a lot of sense. It's profit per unit across the top and max labor hours down. So it really doesn't make sense to bring those two together. This is just going to be, when we plug them in, it's just our profit. That's it. That's it. Yep. So do y'all see, what are we still going to need to find here? We need to find max, but do we know all these points? Because we got to plug them in. The only one we don't really know is this one, right? That's a question mark. Not a very good one, but that's a question mark. So how are you going to find that one? It's the intersection of this blue and the black, right? So I'm going to set up a system of equations. 8x plus 2y equals 400. 2x plus y equals 120. And do you want me to work through it or no? Just tell you what it is? You want to work through it? Yeah? Do you want to kill off the x's or the y's? You want to do the y's this time? So what? Multiply what by what? Bottom by -2. That'll make the y's cancel. So you get a new system. 8x plus 2y is 400. And -4x plus 2y, minus 2y equals -2, whoa, 240. Make sure I did that right.
Yeah.
Yes, okay. My calculus students always make fun of me because I can't do basic arithmetic for my life. All right, so add down. 4x equals what? 160. So x is 40. And if you go back and get y, I believe y is 40 also. So do some work and you'll find y is 40. That all right with you if I don't show that? Yeah. Okay. So this point right here is the point 40, 40. We could label all the other points if we wanted to. This is 0, 0. This corner point is the point 0, 120. And this is the point 50, 0. So what I need to do is take these 1, 2, 3, 4 points, take them and plug them all into the P. Yeah? Okay, so let's plug those into P. May I erase the system or you want me to leave it up? Anyone need that still? So I'm going to do, in no particular order, 0, 0. I'm just going to go around clockwise. 0, 120, 40, 40, and 50, 0. And these are getting plugged into that 90x plus 25y, right? So this is 90 times 0 plus 25 times 0, which is just 0. Yeah, if you don't make any chairs or tables, you're not going to make any money. 90 times 0 plus 25 times 120. Who has that for me? $4,000? Right?
Yeah.
90 times 40 plus 25 times 40. Who has that for me? 4,600? And lastly, if we make all tables, right? We spend the whole day manufacturing tables. How much is it? 4,500. Understand?
So we'll put 4,600 in the box, right?
No, where on the table?
Yeah,
Don't put anything on the table.
okay.
There's not a place for this on the table. So you're not being asked to fill out the table or anything. It's just where's the max? What is the maximum profit? So how many tables should be made? Tables? 40. How many chairs? 40. Profit? If you do it this way? $4,600. That's the way you should do it if you want to make the most profit. What's fundamentally wrong with running your business like this, though?
You're not going to hit that.
Look at